So the last set of intermediate operations we're going to look at in detail at the moment are going to be dropWhile and takeWhile. And you'll see I chose them because they are different in category than the map and flat map and filter operations we've looked at. In particular, map to int, filter, and flat map were all stateless run to completion operations, whereas dropWhile and takeWhile are both stateful. In other words, they have to keep track of the history of what's come before, and short-circuiting operations. So that's one way that things differ. The second way they differ is these are actually operations that were added in Java 9. So Java 9 came out a couple years after Java 8, and in Java 9, they added some additional capabilities. Now, sadly, Android doesn't provide support yet for Java 9. In fact, it probably never will for a variety of reasons. But if you're programming with Java, quad Java, as opposed to the subset of Java that's part of Android, then you can take advantage of these methods. Obviously, we don't use them in our programming assignments that are using Android because you can't use that on the Android platform. So let's first talk about dropWhile. So this has two different sets of semantics based on whether the stream is ordered or unordered. And ordered or unordered is something that is determined by several factors. What type of data is being processed? Is it coming from an ordered collection, like an array list, in which case it's ordered? Is it coming from an unordered collection, say, such as a hash set, which is not ordered? That's one way to distinguish between ordered and unordered. Those are what are called encounter order distinctions. And then also you can actually have an intermediate operation that's used in a stream called unordered. And it says ignore ordering at this point. So I don't care the order in which things will be produced in the final result that comes out of the terminal operation. So if the stream is unordered, if we don't care about the order of the output, then what happens with dropWhile is we will return a stream consisting of the remaining elements in the stream after dropping a subset of the elements that match the given predicate. So as we'll see when we look a little bit further, if you want to skip over stuff up to the point where something is no longer matching a predicate, then you use dropWhile, and it'll basically ignore all the elements that match the predicate. And as soon as the predicate no longer matches, you get back the resulting substream of the elements that follow that did, at least the first of which did not match the predicate. Other ones that come after that might, in fact, match the predicate, but you keep dropping until you hit the one that doesn't match. And so one of the consequences, well, so that's the unordered behavior. If the stream is ordered, if the encounter order matters, then you return a stream that contains the remaining elements in the stream after dropping the longest prefix of elements that match the given prefix, or given predicate. Now, you might go, how does that differ before ordered and unordered? For a sequential stream, there really is no difference. However, for a parallel stream, it makes a big difference. And that's because for parallel streams, they have to keep track of the encounter order in order to be able to give you back the longest contiguous sequence of matching elements in the order that they were encountered in the original data source. And it turns out that this is actually very expensive to compute. It's doable, and the streams framework, parallel streams implementation, will do this, but it's very costly. So the long and the short of it is, don't use the dropWhile intermediate operation for ordered parallel streams. And this is one of the handful of places where there's kind of quirky semantics that work perfectly well with sequential streams, but when you go with parallel streams, ensuring encounter order forces dependencies between the processing, which slows things down. So we'll assume for the sake of these discussions that we're using sequential streams. Some interesting characteristics of dropWhile: the number of elements in the output stream may be less than the number of elements in the input stream. And that, of course, all depends on whether or not the predicates match from the beginning. So if the very first thing you do when you do the first comparison is you find something that doesn't match the predicate, then you'll end up with a stream as output that's the same size as the input stream. However, if the elements that you look at in the stream match the predicate, they'll be dropped up to the point where they don't match anymore. So if there's no matches, then if nothing matches, then you'll have nothing as the output. But wherever the match occurs, the previous elements will have been dropped. So at first glance, you might say, gosh, that sounds an awful lot like filter. Why do we need dropWhile if we already have filter? And the main reason is that dropWhile is a short circuit operation. It'll stop as soon as the predicate doesn't match and give you back the rest of the stream. In contrast, filter needs to examine every single element in the stream. So it's a run to completion operation because it needs to look at all the elements, and it'll only let the ones through that match the predicate. Anything that doesn't match the predicate gets dropped, but we still have to keep going because we have to see if anything that goes kind of to the right of where we found the element that didn't match, if that matches the predicate, and let that one through. So at first glance, they may seem duplicative, but the semantics are actually quite different because one is stateless, one is stateful, and one is run to completion, one is short circuiting. dropWhile also can't change the type or the values of the element it processes. So in that sense, it is like filter because it can't make changes to the type or the values. It can just decide to stop processing once the predicate no longer matches. So we use this in some interesting ways, and I'll show you the source code later, but here's just a kind of a high-level walkthrough visually to show you what's happening with the way in which dropWhile can be applied. So after we have our search results, after we go ahead and run all the other processing, we're going to end up essentially with a list of results that keep track of all the places where the words were found in the lyrics of the song. So we take that list of results, remember this is a list of search results for all the places where the words are found, and we convert that into a stream, and then we collect that stream up into a hash map, and we'll talk more about how this works later, but the hash map's basically going to map the words, like do, re, mi, and so on, to essentially the list of search results where the indices are for that particular word. And then what we do is we take that hash map, we convert that into a stream of key value pairs where the key is the word and the value is the list of result objects to keep track of where the indices occurred. And then we go ahead and we walk through the stream, and what we're doing here is basically called a suffix search. So we're going to go ahead and find, or a suffix slice. We're going to go ahead and skip over everything up to the point where we have a particular word like la, which is like 6th or 7th in the do, re, mi sequence. And at that point, we're going to print from la to the end. And so we skip over everything that isn't la, so we drop the stuff that doesn't match la. And then when we finally hit la, we go ahead and print the results from la to the end, which is la and ti in the do, re, mi song. So that's an example of dropWhile. Let's now talk about the sibling operation to dropWhile called takeWhile. And as we'll see, takeWhile is kind of the inverse of dropWhile. So what takeWhile does is, as long as there's something that matches, we're going to accept it and let it continue down the pipeline. And as soon as we find something that doesn't match the predicate, then at that point, we're going to go ahead and drop everything else in the stream from that point onwards. So that's why it's a short-circuiting operation. Once again, there's this distinction between ordered and unordered semantics. So if the stream is unordered, then it returns a stream that consists of the subset of elements taken from the stream that match the given predicate up to the point where it stops matching. So unlike filter, which keeps looking, as soon as a predicate doesn't match, then we stop and we ignore the rest of the items in the stream. And again, if the stream is ordered, then it has to find the longest prefix of elements taken from the stream that match the given predicate. And this, as before, is problematic when you use it with parallel streams because it has to keep track of the encounter order and coordinate those things across the different threads that are searching in order to find the longest contiguous sequence of matching elements that occur in encounter order. So once before, don't use takeWhile in ordered parallel streams because its performance will be very slow. As with dropWhile, the number of elements that you get may be different from the ones that are in the input stream. If everything matches the predicate, of course, it'll be equal, but if you reach a point where there's no match, then everything from that point will be ignored. As before, the semantics of takeWhile differ from filter because takeWhile bails out as soon as the match doesn't occur with the predicate, whereas filter has to look at everything in there. Also, like dropWhile, this is kind of getting redundant, you can't change the type or the value with takeWhile, but you can filter things out. So we could use takeWhile to do essentially what's called a prefix slice, where you might say, I want to print all the results in the output starting from the beginning up to, but not including a certain word. So if we do this particular operation, which is a prefix slice, and you say print everything up to la, it'll print do, re, mi, fa, so, and then it'll stop at la, and it won't print la and ti. And as before, same basic idea, you convert the list of results to a stream of results, collect everything up into a hash map that maps the search words to the locations where the words were found, convert the hash map into a stream, and then continue to take the elements and process them up to the point where you hit a match. And in this case, we invert this, so you keep going while something is not equal to what you're looking for, where you want to terminate the stream. And then at that point, when you're done, you print the results out. We'll take a look at the source code in more detail later, and I think you'll have a better sense of understanding how it all works. But it's a very cool operation if you need that kind of short-circuited, stateful-based semantic. So that's the end of the discussion of dropWhile and takeWhile. I mostly put these things in here, not so much because you're going to use them in your programs, because unfortunately, using Android limits us in that respect, but because I think it's interesting to see examples of stateful, short-circuiting intermediate operations to compare and contrast with the stateless run-to-completion operations we looked at earlier.